In this tutorial, we're going to talk about the seismic analysis for buildings using the Equivalent Lateral Force procedure of American Society Civil Engineer Standard. As any project, the first thing to do is gather the basic information, which is divided in these 6 steps: soil analysis, type of structure, risk category, importance factor, seismic design category, and design of base shear. Soil analysis. The soil report for seismic analysis purpose will show us the soil classification, the site class based on the average of shear wave velocity, the average of field standard penetration resistance, the average of the standard penetration resistance, and the average of the undrained shear strength, as requested on Table 20.3 and -1 of American Society Civil Engineers Standard. Also, will show us the mapped acceleration parameters SS and S1 for short and long response acceleration, and the long period transition period, which we are going to calculate the site coefficients FA and FB for the short and long period, the expected response acceleration SMS and SM1 for short and long period, and the design expected acceleration parameters for short and long period, SDS and SD1. Type of structure is a structural system that we already chosen and is being designed in accordance with the architectural professional, architectural requirements, and high limits, according with American Concrete Institute, American Institute of Steel Construction, and American Society of Civil Engineers Standards, which we are going to determine the appropriate response modification coefficient, overall strength factor, and deflection amplification factor, in accordance with Table 12.2 and -1 of American Society Civil Engineers Standard, which could be building wall system, building frame system, moment resisting frame system that is subdivided in ordinary moment resistant frame, intermediate moment resistant frame, and a special moment resistant frame. The other systems are dual system with special moment frame, dual system with intermediate moment frame, shear wall frame interactive system, and a steel system not detailed for seismic resistance. Risk category is a classification according on the risk to human life, health, and welfare associated with their damage or failure by nature of their use, and should be determined according with Table 1.5 and -1 of American Society Civil Engineers Standard. And there are 4 types of categories. Category Level 1 are for buildings that represent a low risk for human life, such as agricultural facilities or storage buildings. Category 2 are for buildings that represent an intermediate risk for human life, such as house, apartment buildings, or stores. Category 3 are for buildings that represent a substantial risk to human life, such as a school. And Category 4 are for buildings that are designated as essential facilities, such as a power generating station, police and fire station, and hospitals. Importance factor is a safety multiplier to increase or decrease the design base shear according with the occupancy or use that depends on risk category according with Table 1.5 and -2 of American Society Civil Engineers Standard. And their value is for risk category 1, 1, risk category 2, 1, risk category 3, 1.25, and risk category 4, 1.50. Seismic design category is a classification assigned to a structure based on its occupancy and use, and severity of the expected response acceleration parameters, and are classified as A, B, C, D, E, and F, as illustrated in Tables 11.6 in -1 and 11.6 in -2 for short and long period respectively of the American Society Civil Engineers Standard. Also, we need to have in consideration the horizontal and vertical structural irregularities as shown on Tables 12.3 in -1 for horizontal irregularities and Table 12.3 and -2 for vertical irregularities of American Society Civil Engineers Standard to determine the proper seismic design category. Design of base shear is the total lateral force which the horizontal seismic ground motion is considered to be imparted to the structure and is calculated with the equation 12.8 in -1 of the American Society of Civil Engineers standard, where V is the design base shear, CS is the seismic response coefficient, and W is the effective seismic weight. The seismic response coefficient, CS, is calculated with the equation 12.8 in -2 of the American Society Civil Engineers standard, and the effective seismic weight is the total weight of the structure plus the dead load added from the construction materials incorporated to the building, and shall include a minimum of 25% of live loads in areas used for storage, as requested in section 12.7.2 of American Society Civil Engineers standard. Now, as example, we are going to apply the equivalent lateral force procedure for a special moment-resisting frame structure of 4 stories for a residential use with these features. Total height 480 inches, height of each story 120 inches, slab thickness 10 inches. The area of the building is 400 inches by 350 inches, 12 columns with dimensions 12 by 12 inches for corner columns, 12 by 40 inches for border columns, and 14 by 14 inches for central columns. The load-bearing beams with dimensions 12 by 14 inches and the anti-seismic beams 12 by 10 inches. The first thing to do is calculate the effective seismic weight of the building, taking in consideration the slabs, columns, and beams that belong to each story. The slab shall include a part of its self-weight, the construction materials incorporated. In this case, it is necessary to use live loads because the building hasn't a storage floor. The dead loads for the roof story per unit area is 0.960 pounds square inch, and for the structural floor story is 1.154 pounds square inch. The total weight of the roof story is 159,310 pounds, and for the structural floor story is 192,630 pounds. The total seismic weight for one roof story and 3 structural floor stories is 737,170 pounds. The next step is calculate the seismic response coefficient, knowing that the building is for residential use, which means the risk category is 2 and the importance factor is equal to 1. The data obtained from the soil analysis give us a site classification C, the short period map acceleration parameter 1.5, the long period map acceleration parameter 0.6, and the long period transition period equal to 12 seconds. With this data, we verify in the tables 11.4 in -1 and 2 the short and long site coefficient, given 1.2 and 1.4 respectively. Now, we calculate the short and long spectral response acceleration SMS and SN1 with equations 11.4 in -1 and 2, resulting in 1.8 and 0.84 respectively. Now, we calculate the short and long design spectral acceleration STS and SD1 given 1.2 and 0.56 respectively. In the table 12.12 in -1, knowing that the building design is a spectral moment resistant frame, we select the proper system that is special reinforced concrete moment frames, with a value for response modification coefficient of 8, over strength factor of 3, and deflection and amplification factor of 5.5. Now, we calculate the fundamental period with equation 12.8 in -7 of the American Society Civil Engineers standard, where the coefficients CT and the powered X from H are determined from tables 12.8 in -2, and H is the height of the building in feet. In our case, for an reinforced concrete moment resistant frame system, the value of CT is 0.016 and X is 0.9, resulting in a fundamental period of 0.442 seconds. Finally, we calculate the seismic response coefficient with the equation 12.8 in DAS2, giving a result of 0.15. We need to verify that this value not need to exceed the equations 12.8 in DAS3 and 12.8 in DAS4, depending on the long period transition period. In our case, we use the equation 12.8 in DAS3, where the condition is the fundamental period is smaller than the long period transition period, giving a result of 0.158. We use 0.15. After has calculated the value of the seismic response coefficient and effective seismic weight, we can calculate the seismic base shear of the structure with the equation 12.8 in DAS1 of American Society Civil Engineers Standard, giving a result of 110,575.5 pounds. Now, we're going to do a vertical distribution of the seismic force, according with the equation 12.8 in DAS11 of the American Society Civil Engineers Standard, where Fx is the lateral seismic force induced at the static level, Cxb is the distribution factor, and V is the seismic base shear. The distribution factor is calculated with the equation 12.8 in DAS12 of the American Society Civil Engineers Standard, where W is the seismic weight of the static level, H is the height of the level as studied from the base, K is a value related to the structural period, 1 for a period less than 0.5 seconds and 2 for periods between 0.5 and 2.5 seconds. The summation is the sum of the total value that results from multiply W by H of each history. The final distribution of the base shear to each history is for roof history 38,265 pounds, structural floor level 3 74,420 pounds, structural floor level 2 98,524 pounds, and structural floor level 1 110,575.5 pounds. Notice that the value of the structural floor level 1 is the same as base shear, which means the distribution was done right. With this, conclude this tutorial.